But yeah, now it's getting better. Okay. So my presentation today is Emergent Multifidelity Service Systems. As usually, you know, my occupation is very confused because I work in many different places, but most of the time I work at, for the past 10 years at Wright-Patterson Air Force Base.
I'll put that a little higher, and then it might work.
I don't know. One is for translation, for interpreting, I was told. So I don't know which one is for what.
Oh, you have two.
Yeah, yeah. So they hear me well.
This one?
Yeah. Oh, he says don't touch.
This one works.
Okay, can you check? Yeah, okay. So, since, you know, we lost already 5 minutes, I will try to go as fast as possible. So I will tell about myself, about Wright-Patterson Air Force Base, where I work, and I work only in Polish-Japanese Academy of Information Technology 1 week per year. I teach one class only per year. I come for a week and I teach every day 5 hours, and that's it. So I am the 99% in the United States for 29 years, okay? So I was working 18 years in Polish Academy of Sciences. By the way, I graduated from LETI in St. Petersburg, then worked in Polish Academy of Sciences, and from 1989, I work in the United States. And I was leading many large projects in the States, DISTOC, DARPA Initiative in Concurrent Engineering, that was West Virginia University. The university got $100 million grant for concurrent engineering. I was leading knowledge-based integration. Then I was invited to join General Electric Research, Global Research and Development Center. I was leading large projects like ChemNet, Agile Castings, World-Class Engineering, and FIPER was the last. That was $21.5 million founded by NIST. And after that, I joined Texas Tech University, and I was leading my lab, SORCER, Service-Oriented Computing Environment. And I started from 2002, and that technology was used, they started using basically in 2002 to design the next generation of American military planes. And basically I continue after Texas Tech to help basically my colleagues who worked before with me in GE Global Research Center. We applied the technology, federated intelligent product environment, to design optimal engines for General Electric. And currently we use the technology to basically design the whole optimal airplanes at Air Force Research Lab, including obviously materials that are based on nanotechnology for airplanes, really. So that's shortly. Obviously, I work also in China. SORCER is used to design, for example, fast train in China, and I collaborated for the past, I think, 10 years with Beihang University, which is leading aerospace university in China, and Jiaotong University, that design fast train in China. So a few words about Air Force Research Lab. Because the name is Air Force Research Lab, people think it is a kind of laboratory. It is a very huge organization. It has 40 locations around the world. I work in headquarters, which is in Dayton, Ohio. That's Wright-Patterson Air Force Base, the largest Air Force base in the States. 30,000 people work over there. Section B is only for research with highly equipped computing infrastructure, many supercomputers, obviously, dozens of clusters and thousands of computers. And I work in Aerospace System Directorate. We have many directorates. Over there, as you see, material and manufacturing is still there, and obviously nanotechnology heavily used over there, but everything is focused basically to design aerospace systems. Next slide shows basically what we do. So we do discovery, development, demonstrate solutions, and deliver basically everything what flies in America with the goal, that's about, now I'm talking about Aerospace Systems Directorate only, okay? So aerospace vehicle focus technologies to ensure warfighter and air dominance, basically, in the world. So let's see what I skipped. Yeah. So that's only, again, the directorate that I work. That directorate currently has 580 programs, about 2,000 people working. You see distribution. There's master degree, PhD, bachelor, almost 1/3 in each category. We have 50% contractors, only 7% military employees, and basically about 40 civil employees. Directorate is in 2 locations, basically. As you see, 1917 was created at Wright-Patterson Air Force Base. By the way, Wright brothers designed and tested the first place in that area where Wright-Patterson Air Force Base exists. There is beautiful Air Force Museum at the area of the base, including all generation of aviation over there. And the second part is basically those are rockets for aerospace systems in Edwards Air Force Air Force Base. What the problems we are facing here? Obviously, the conference is IT and nanotechnology. They do not exist without each other. Obviously, we have seen presentation, basically folks coming from materials and creating from existing materials new materials. My colleagues design also in the reverse direction. They create physical models at atomic level to create new materials based on physics. And eventually, if such material is found to promise required properties, for example, for airplane. For example, this is a small UAV. As you see, this is a plane that fits on the finger. That's the finger, basically. So you need special materials to fly planes like this. So the technologies we are using to design are not typical based on historical data. Okay, so those are extreme environments planes. Those are large deformations planes that during flight they change geometry, and obviously very, very small for reconnaissance. Basically, they fly in the network. They have a video camera. You can get basically information about large area, very detailed information. So in order to design planes now, we need basically fly higher, far away, basically faster, and at the same time lower, close to each other, and very slow, like those. So that causes that we need really innovative solutions. And those innovative solutions are not really cheap. As you look, here you have the chart. Air Force Research Lab requested DARPA, Defense Advanced Research Agency, for that study why military planes are so expensive. Okay, and as you see, for example, F-22 was designed about 22 years. V-22, that's Osprey, was designed about 25 years. I mean, the time from years from start to initial operation, and that's the time in history, basically. As you see, F-16, which is used like in European military, that was 5 years from design to full deployment. And now we cannot do this within 20 years. So the government said, hey, Air Force Research Lab, no more money. You cannot design 20 years new airplane. Okay? And the study shows basically that, for example, when you look at commercial aircraft that you are flying, basically, the time basically increases a little because of new materials introduced only. And the design is based on historical data. Those planes are almost the same, only some small improvements. Okay? If you look at the cars, introducing new car, basically now is 2 years. You have completely new car. Because again, cars are based on historical data. All the stuff, as I told you, I show you, very different airplanes are based on innovation. Each airplane is completely new design. There is no historical data if there is no historical data, you have to basically check all possible options how that plane can be used. And still, like F-35 is designed so long, but it is not based on physical models. Okay? And you cannot cheat physics. If something is not consistent with physics, it will break. If it breaks, you have to redesign, and that's the reason it goes 20 years to do this. So basically, we are trying to do this running as much as possible, including physics at preliminary design. That's what basically, and including all disciplines. So merge conceptual and preliminary design. That means preliminary design based on physics. And we are adding all those disciplines. I switch basically, as you see here, like all of those. And for that, Multidisciplinary Science and Technology Center was created at Air Force's Research Lab where I work basically. And SORCER is used basically as a basic computing platform for in Multidisciplinary Science and Technology Center. So we include all those domains, including nanotechnology, obviously, and we try to find optimal solution, but not optimal solution for one design. We consider, thousands of design, but we don't want to analyze each design. We want to run one design that includes basically thousands of even millions design. That means it's a system of systems, okay? And for that, basically, we need new computing methodologies. And that's what basically the summary. It's just, I said basically. We create technology suite, we create conceptual design, but conceptual design has thousands of configurations. Then that conceptual design has tens or hundreds modeling and design configurations. Then we use different fidelities of the computing models, because if you go with full exact physical models, you would calculate probably that 100 or even more than 100 years. So the challenge is how you want to optimize the whole engine in reasonable time. Not 100 years, nobody will be waiting for that, okay? So, and then basically that's design space exploration that we are running. And from that, basically we change technologies. For example, if there is no adequate material, folks are trying to synthesize and eventually make this physically available, such material. But everything is driven by, and that's basically new methods applications, new technology validation, and so on. So basically, in multidisciplinary science and technology, we work in 3 teams, basically, and I work in all of them, really, because they need the computing power everywhere. And that's, so the focus is get more and better information and get it earlier. If you get that information earlier, probably you will avoid those problems developing over 20 years a new design, new airplane. So, so technology, obviously, I will not go into details. Technology is the issue here. Then engineering capability impact is obvious, but we are not trying to optimize airplane from this point, from engineering point of view. The optimization goes for mission capability impact. So the government specify requirements, what is needed for defense, basically, and we optimize new airplanes for those characteristics. Those characteristics imply what engineerings are needed, basically, and that implies basically what technologies we can use. So I'm trying to emphasize that optimization criteria change, basically because they are mission-driven. You design not just airplane, but for a particular goal to achieve particular mission. So the goal is, all that research I'm doing is basically in the center, Multidisciplinary Science and Technology Center, basically deliver vehicles that satisfy mission requirements in a timely manner, reduce the number of late defects due to model-led physics, that's basically go from 20 years let's say to 5 or 10 years eventually, and trace technology to, that's what is meant, to mission level capability impact based on physics. So what government specifies, that's the capability, and basically create physical models to make this as robust as possible, the design robust as possible. And that caused that our approach is based on transdisciplinary approach. It is related to how you basically create computing systems. As you see, everywhere those arrows are solid, here are basically dashed. That means the computing environment is not fixed. No static connections between computing elements in the system. First of all, they are network-centric, so they are in the network, and how they are connected really, how computing program is connected, is specified basically at the solution level. So we don't want engineers to be involved in programming, writing code, because currently most engineers complain they do like 60–80% computing work. What computer scientists have to do. But engineers are not trained to write good software. So basically, the service modeling language that we have developed and continuing for decades already, basically, is designed for engineers that basically in a few minutes from existing services, you can create a new model and start almost instantly computing it. Okay, so engineers are focused on engineering work, and computing part is done basically by computer scientists. And that legacy is huge. Like when we started FIPER in General Electric Research and Development, when I visited aircraft engines, they said, look, for aircraft engine, we have 30,000 programs written. We lost control. What programs we have, people are leaving, you are coming, redoing the same programs, it is mess. So the concept is to put all those programs, available resources in the network, and create a program that will find those programs needed, install if they are not in the network, and run everything dynamically. So all connections here, the core program that consists of any engineering modules is done dynamically. And for that you need the right operating system. In order to have this dynamic very efficient, you need multi-fidelities. That's what engineers call n-squared matrix, basically. But we want to run this with multi-fidelities. For example, if we will compute arrow, up and away arrow, you can create calculations based on empirical model, linear potential, Euler, Navier-Stokes. Those are different physical models, but the difference is that empirical runs very fast, but precision is 30% from our studies. All those models that have been used for F-35, they have precision, as we know now, based on physical model, 30%. That causes that breaks continuously, and you have to fix. But if you go to the high fidelity models, it takes, as I told you, years, or even tens or 100 years to calculate. So the problem is that all computing elements in the system have multi-fidelities. And multi-fidelities, basically, are selected at runtime. Each fidelity, what we call, has morpher. Morpher watches the intermediate results, and based on the results, selects fidelities in the system. Okay? That we call reconfiguration. So you run the system and reconfigure for optimal solution. But on the top of that, we have also meta-fidelities. Those are fidelities of fidelities. And meta-fidelities create a new system. So we have meta-system, system of systems. So we don't want to optimize one system that can be reconfigured. We want to find the optimal system, basically, which is optimal system from all thousands of systems available. That's basically exploration based on multi-fidelities. So you create really one meta model, and that meta model might have basically 10 or 100,000 of systems, but we want to optimize everything at once, basically. And take into account that when you go to high fidelity physics-based model, the number of variables grows from thousands to millions, and currently we have models that exceed billions, multi-billions of variables. Okay, so you cannot compute this even on supercomputer. You have to spread this across collaborative, basically, computers in the network. And obviously, yeah, as I said, this is network-centric. Air Force Research Lab, by the way, in Dayton, Ohio, is surrounded by hundreds of companies because Air Force Research Lab provides basic science, basic study for all those companies like Boeing, Lockheed Martin, Northrop Grumman, and so on. All those companies work together. All products that fly in the States are made by hundreds of companies, but leadership is by Air Force Research Lab that provides basic research because those companies don't want to do this. They don't have money. So that's you know, very fast. The focus is basically in my research all the time on process expression and actualization. And currently, computer science is defined really as a science of process expression. We started, you know, in the past with notion of algorithm, and we are beating the notion algorithm all the time. And it is so low level that you cannot create systems like we need for network-centric computing, which are not algorithmic. Those are socio-technical systems. And basically, the notion of algorithm is now basically synonym to process. If you know, but as you know, Markov defined the notion of algorithm. It was mathematical concept that was final, not deterministic, and so on and so on. And after that, if you cannot do with that notion of algorithm, you say stochastic algorithm for another. So the notion of algorithm got devaluated completely. So it is just process definition. But we knew you have to find the right process expression. And I will go faster. Basically, that's basically, those are process expression languages. In most cases, those are domain-specific languages. And we are focused on service modeling language that has roots or methodology like UML, Unified Modeling Language for object-oriented computing, basically. And then, basically, that's SORCER operating system that basically interprets problem domain created by engineers, not for computer scientists. Those are what software engineers do, not this, basically. And that basically integrates executive codes. And that's the knowledge that was accumulated in many organizations for, let's say, decades. 20, 30 years, we have a lot of code. Code that was written in Fortran, let's say 10 years ago, still is used over there. The issue is how to incorporate all those programs written a few decades ago. I will go faster. So instead of that n-squared diagram, we are using n-cubed diagram. So it is like diagonal, this is n-squared, but you see in the square we have all nodes with multifidelities. That means if you compute any value, there is always multiple ways to do this. And in particular, when you do initial calculations, you go with low fidelity because you can calculate this faster. But when you come to optimal solution, you want to use exact models at the end, when really is very time-consuming computation. That's the service-oriented terminology, because in service-oriented computing that we use, you know names, microservices, all the stuff, there's nothing really, doesn't have any common with service-oriented computing. Like in object-oriented computing, everything is object. In service-oriented computing, or true service-oriented, everything is service. So we have basically, that's the process expression. We have front-end services, we have back-end services, and we have operating system basically services, which is basically actualization of the service modeling language. So we have operation services. They are signatures. So signature is a kind of reference to a service provider. The service provider can be anything. That can be in the network procedure, local procedure, evaluator, everything, and there is no static connections. So those are real, like microservices. Provider service is really microservice, but the connection between microservices is done by the end user, not by a computer scientist or software developer with API. Okay, so that's the big difference. That we have request services that are for end users, and we have basically provider services where you use APIs and programming languages, and the operating system that basically allows you to manage very big federations of services in the network or local. It doesn't matter. Signature basically looks the same for local or remote call. The difference is only if you use how you use service types. If those service types are interfaces, then everything is found in the network by the type. There is no naming conventions. There are really multi-typing. You specify multi-types implemented by a component, and you can find that component. If not, that component will show it automatically in the network. I will go faster. Those are compositions. I will not go basically into details because there is no time to describe basically implementation and semantics of SORCER, but that really picture shows basically how we integrate all computing. As you see here, in each color we have basic 3 operating systems. That means like Unix style, object-oriented Java, basically, and SORCER is green, and SML is basically service modeling. The issue is that the notion in conventional computing is based on subroutine. I mean, subroutine is a function, procedure, anything that we use in regular programming languages that you create executable code. And object-oriented programming, as you see here, that's basically that's the function, instruction, basically. A procedure is aggregation of constructions, and object is aggregation of methods, and service orientation has completely different semantics. I mean, true service-oriented semantics, as I mentioned, you have basically those requests, you have service providers, which lies in conventional, but signature you can link basically to the service provider local or in the network, or you can connect, you can bind to any object and, for example, invoke the method, or you can basically use entries that use different types of evaluator subroutines. So you can invoke everything from service-oriented computing. The concept is that basically we look into the computing as a evolution process, like building cities. If you build a city, something that was built 100 or even 200 years ago in the city still exists. You cannot build new city from scratch, like you cannot build computing system, large complex computing system from scratch. You have to utilize what existed before. So that's the reason here is the aggregation of those 3 colors. 3 operating systems are integrated, including the semantics of services. And that requires the culture change, basically. Currently, people are focused on conventional programming, creating, in most cases, imperative code. When complexity increases, you have spaghetti code. That's the reason object-oriented was created, to untangle, basically, that spaghetti code into smaller methods combined into the method. So still you have basically imperative within the method. But the difference is that that's what I teach, and sometimes, I don't know, deal with students and they take object-oriented courses and they don't know, and I ask, show me your inheritance design, polymorphic design, and they don't know what I'm talking. They say, I create a class and I have methods. So they write basically methods as much as is algorithm, and that's it. If you look into basic object orientation, there is no notion of algorithm. So if you don't design for encapsulation, inheritance, and polymorphisms, you don't really do object-oriented design. And that's the reason we have been trying to specify those pillars for service-oriented computing, and I will show you basically again the picture later, but that's the culture, but we are reversing everything. We basically, I will skip this. Oh, those are, but where I have this? I lost. Oh, that's the traditional culture. We are reversing. We go from service-oriented computing, design basically service-oriented environment. Then for that, we design object-oriented systems, especially service providers. And in those service providers, we introduce basically algorithmic programming as basically methods in those objects that sit in the network or are used local. But the programming starts from the top down, this way. And that basically requires change of the culture, programming culture, and the center was created basically exactly for doing this. If you cannot change culture, you cannot really change the way you are building complex systems. Let's see. I will skip this. And that's basically, as I mentioned, the evolution. Basically, we look into what we call the programming gate. And those are structure programming pillars. On that, we have basically object-oriented pillars. And those are 3 pillars of service-oriented programming. Take into account that basically each pillar encapsulation is supported by block scoping. Encapsulation object-oriented supports contexting. In service-oriented computing, we use service context as one argument for everything. So data flows as a one single data structure. So encapsulates everything what is needed for service, including what was considered in object-oriented programming. The second pillar basically is related to control flow. We know that algorithmic logic specifies branching and looping. That's basically the whole concept of algorithmic logic. Object-oriented includes basic polymorph as a control strategy, basically. So for example, if I see if then else in object-oriented program, that means those guys do not understand what is polymorphism. Okay? And if you don't design for polymorphism, then you if then, else, and so on. That's basically coming from here. And here we have multifidelity, as I mentioned, that basically it is polymorphic behavior, but not related to subclassing, to inheritance, because polymorphism in object-oriented is based on inheritance. Here, multifidelity is basically created based on concept that you have realization of the same function, multiple realizations. And in the paper, I was trying to write, because when I teach that, students say that the most difficult is terminology. It is very difficult to understand and differentiate those 3 layers, basically, because everyone is coming with baggage, and everyone assumes that if I know object-oriented, I do everything. Yeah, it is generic, but when complexity grows, you are lost. You cannot express that complexity. Okay, so multifidelity is the key, and that morphing and emergent behavior of the system is basically based on multifidelity. But this is a polymorphism for a computing component, generic computing component. And federalism is created that basically like here we have block basically nesting, how you compose larger computing components from smaller. Inheritance is basically in object-oriented, and federation is basically network-centric federation. Network-centric federalism. That means that you can combine the same way local component and remote component the same way. And when you design your model, you don't care if that component is local or remote. It should, in programming language, be expressed the same. An operating system takes care if that component will be used locally or remotely. It depends how you specify signature. And you can swap in signature remote local, and the user doesn't need to know anything about networking or security. Everything is taken care by the operating system. I don't know any other operating system like this, and that's the reason, it is difficult to teach, because nobody teaches that approach. So that's the basically programming that we follow, and as I explained, we go from this layer down eventually. If you have everything done already here or here, then you just do engineering work as needed. And here I describe basically all those 3 pillars in details. Here I will emphasize you have the green basically. If you know object-oriented programming, you know UML, you know that basically the whole conceptual framework in UML comes from meta-object facility. In service-oriented computing, it comes from meta-service facility. In object-oriented modeling, you do with UML. In service-oriented, you do with service modeling language that I told you. We are developing this over a decade, and it grows every year, basically. Here you create object-oriented model. Those models in SORCER are called Mograms, because we do not differentiate model from program, really. Because the division comes from that in the past models have been conceptual, not executed. Okay, program was executed, but now we create models which are declarative, and they are executed. So there is no difference really between model and program. So you can create program that might have multiple models inside, and model that might have multiple programs, and everything gets executed. So the term for model or program is called really Mogram in computer science. So we call the service Mogramming, and we have a scripting language, so we can write a script like C script, for example, and run hundreds services in the network related by those signatures, which are references to services in the network. And here you have your SORCER platform, basically object-oriented, and object-oriented platform serves as a basically carrier for service federation. So service federation, when we say federation of service providers, those are really remote objects or local objects connected basically by operating system. So in parallel, we have basically the same structure that was designed for UML, and I had opportunity to work for 5 years at object management group that developed UML, and I was part of the team while I was working at GE Global Research Center. I represented Global Research Center at Object Management Group, and I was a technical committee. So that's the reason I'm familiar with all that process that was created for object-oriented, the same way I did for service orientation. And that's basically the conceptual, scheme. Those are request services. So engineer create in SML Mograms. Those Mograms are passed basically to SORCER, which is distributed operating system. Again, it is collection of services. You replicate those services up to 5. We never run more than 5 with 5 services, either those used by operating system or those created or provision for the user based on declaration. Basically, those services are replicated to 5, and with 5 you have 99.99 probability that one exists. Okay, because they are equivalent, really. They represent types, and you will find by the type, not really by instance, specific instance. You don't know where you are connecting to what computer or where that program will be deployed on what computer. User that creates the model doesn't care about this. And those are more UML diagrams that describes in details. Here I emphasize 3 agilities that we use here. So I told you we create meta system Mogram that basically has meta fidelities, and for those set of meta fidelities, one set or one meta fidelity, let's say meta fidelity of the system, it sets fidelity. So we have system Mogram, we execute, service federation is created. Basically, fidelity manager watches the results and eventually reconfigures. Oh, my battery died. So you have one loop here, which is reconfiguration. You are running and really executing or optimizing the same system. But if fidelity manager decides that different meta fidelities should be used, we create really a new system. That's a system of systems. 2 minutes, yeah? Okay. Here I have basically a test case I wanted to show you, but there is no time. I can run this. So as a test study that I was doing last year, basically to demonstrate really for the management at Air Force Research Lab how fidelities can be used. We selected 3-bar Truss optimization that was solved basically in early 60s. mathematically, but not computationally with computer. And basically, we designed this with service orientation, with all those providers, with multi-fidelities, like a planar truss provider that has those bars in one plane, but with different multiple ways to calculate finite differences, direct or adjoint, or with different tools like Astros and Nastran to create again the same stuff differently. Depending on the fidelity, you can run. That's the mathematical model, and those are 3 bars basically connected here. Those are requirements. Those are basically mathematical formulation, constraints, everything. That's optimization. And basically, we are running this in the SORCER exploration framework. All those services are available, or just we run multi-fidelity optimizer. So it is successive optimization with approximator. This is what is called outer loop, and you have inner loop with different fidelities or approximation. In many cases, basically, fidelity is interpreted as approximation. And you can run basically depending how you calculate sensitivities and values of the variable, a few minutes to a few hours. And from that we are learning basically what should be improved, how to calculate fidelities. If that system, like we are using MDA, multidisciplinary optimization with coupled systems, you have multiple systems, what you have coupled variables, and you have to calculate global sensitivities. We can calculate global based on chain rules. So all engineering work can be calculated. Only the difference is, that's what I mentioned today, that you can calculate basically outer loop minutes to days. Okay, the last probably. So only SORCER that I developed basically initially at General Electric Research and Development at Texas Tech is publicly available. All the stuff that we are doing, SORCER modeling, which is VAR-oriented and engineering open, is open, but for collaborative efforts, research lab, and the next 2 layers of SORCER are classified, not available at all. So if you want to try to create your own environment, you can start from public open source, which is on GitHub. That's it.
Thank you very much. Thank you. In particular applause, he was still in time, so we have time for questions.
Wow. Any question?
Please.
Yes.
The beginning of your presentation, I'm really interested what happened in 1975 that development of new airplanes started to be so expensive. So this is
they have been very simple. I have another chart because they have been not complex system. We define, and therefore system of complex system is above 10 million lines of code. Okay, so if you look like, okay, yes, so F-16 has only 300,000 lines of code. 80% control is mechanical. Okay, in F-35, 90% of control is in software. Okay, F-35 has 18 million lines of code. Okay, and still we have 1,500 errors, software errors, and testing. If you take testing of that amount of code with regular software engineering methods, you need 100 years to fully test. And the government said, no more testing. You have to develop the hierarchical design software system with no conventional testing, all inputs and all outputs.
Next question, please.
So software, yeah.
Really no more question? Okay, then we thank the speaker again. Thank you very much.
Institute of Applied Physics belongs to the Academy of Science of Moldova and was founded in 1964. This was a former, the Academy of Science of Moldova was a former filial of Academy of Science of Soviet Union, and from the 19th we are independent branch of the academy. But from that time, several scientific school was being established as our foundations of this school was studied in the Russia, and this is physics of non-crystalline solids, crystallography, electrochemistry, physics of semiconductor materials, and kinetics physics. And this this is a seaside of our country, Chisinau, and this is entrance of our Institute of Applied Physics. Welcome. And the area of research of our institute is fundamental and applied research in the physics and the physics chemistry of condensed matter and crystalline and non-crystalline materials, and optoelectronics and photonics device then. And our laboratory material of photovoltaic and photonics. And my group in this laboratory is occupied by physics and engineering of chalcogenide glasses of photopolymers, photonics, and optoelectronic devices. And investigation of chalcogenide glasses was begun by academic Andriesh in the Moldova from the St. Petersburg's Institute of UFA, and now we continue their work and their investigation. And this is the staff of my groups in our institute. And our short outline of my presentation, motivation of this experiment, result before the conclusion. At first, motivation and development of micro and nanoelectronics required as materials for this for the recording of the different diffractions and optical structures, and new method for manufacturing of these optical elements. And about the methods, in contrast, the scalar holographic process, polarization holography employs beams with two different polarization states for hologram recording. And in this case, the phase difference between the interference waves leads to changes only in the polarization states. And intensity modulation is absent in this case, and only the polarization state modulate in the materials. And this idea to record as the polarization, or other is the name vector hologram, was the idea was first expressed by Kakichashvili, scientist from Georgia, Kakichashvili, in 1972. And it was realized, this idea then on the by the recording the vector hologram on argentum chlor glasses. And the theory was being developed by Kakichashvili, but I have to say that the theory of the optical conventional holography is complicated, but the theory of the polarization holography is more complicated, because you have the one more variety in your hologram. But the advantages of the polarization holography, the many advantages. And polarization diffraction gratings is useful elements for fabrication of polarization discrimination system. This is the main application. You measure the Stokes parameters and use in the different spectra photopolarimeters devices. And then interesting properties of this hologram, the theoretical value of diffraction efficiency for vector hologram can be reached 100% theoretically. And by the vector hologram allow using all the features of the light, as amplitude, as phase and as a polarization. And so you add one more capacity for the holograms. And about the materials, the chalcogenide glasses. This is amorphous semiconductors, which meet the polarization sensitive requirements. I have to say that to have the not all materials using for recording can be used for the polarization recording, and chalcogenide glasses can be used for the polarization recording. And amorphous chalcogenides are why? Because amorphous chalcogenides are intrinsically metastable, and such can be easily modified by external action, by the light in particular. And the effect of photo-induced structural changes is mainly used for holographic recording in chalcogenide glasses. There may be many composition of chalcogenide glasses, and elementary holographic gratings in chalcogenide glasses are generally recorded by specially modulated light intensity and light polarization distribution. And so many applications of holographic gratings in optoelectronics has mainly been based on their transparency in infrared up to 10 micrometers as a passive elements, and a sensitivity to different kind of radiation as active elements. And the later produce the many structural changes in these glasses. This is changes in absorption, in refraction, in transmission, and in the topology of the surface. And what is interesting that what all of this may be in the direct without any additional treatment of these materials. And the drawing of the optical fibers from chalcogenide glasses, the same were studied in our lab. And this is a map of the investigation of chalcogenide glasses from the America and up to Japan. And in the Europe, many scientific centers are devoted to the investigation to chalcogenide glasses, because there have many applications. And why the chalcogenide glasses exhibits many kinds of photo-induced phenomena. And from the electronic point of view, the glasses is a kind of semiconductor with the energy gap between 1 and 3 electron volts, and so they can be photo-induced by visible light. And then excited carriers are effectively localized in disordered and defective glass structure, and so these carriers undergo the strong electron-lattice interaction. And from structurally point of view, these glasses has moderate atomic connectivity. They are not so rigid as oxide glasses and not so flexible as organic polymers. And for instance, typical arsenic 2 sulfur selen 3 have disordered covalent layer with coordination number between 2.4 and 2.67. And then the glass transmission of these materials lies in the range from 200 up to 400 degrees, and so they can be more stable in the room temperature. But up to now, detailed mechanism of each photo-induced phenomenon have not been elucidated in these materials, and so this is the reason to continue the study of these materials. And one multilayers. The multilayers in chalcogenide structure, this is the simplest artificial nanostructures that can be rather easy fabricated with control the geometrical parameter and investigated as a thin films. And this glass is promising for the nanostructuring because the control of nanostructuring could give the information about the structure of these glasses. And these glasses may yield a wider variety than the crystalline, because now the restricted bonding conditions exist for the crystalline contrast in the glasses. And so the structural variety, you may diverse the composition to formation nanostructure sensitivity to different ranges of the weight of the light, and so you may vary your device sensitivity. Experimentally, the surface relief grating formation is usually studied using the diffraction efficiency method in condition of absence of other reasons. And so the aim of our work is to explore the light-induced polarization-dependent one-step phase relief grating formation in chalcogenide, nanomultilayers, composition arsine, sulf, selen, and compare with amplitude holographic recording. And to study how the polarization state of recording beams and the period of recording gratings influence on the diffraction efficiency, the main characteristic of the grating of the formed structure. And about the samples, we modified the thermal vacuum deposition method for two glasses evaporation in the two isolated boards with constantly rotated on the substrate through the mask, and so we can form the nanomultilayers, and in the one process we can form the we can obtain the any kind of the layers introducing in the in the structure. And this technology allows depositing thin film with thickness from 5 nanometers to up to 3 micrometers. And we can control the thickness of each layers during the vacuum evaporation process. And this layout of our nanomultilayer samples. In the center part of this is a pure selen. In the middle part, this is a nanomultilayers arsine, sulf, and selen. And in the outer part, this is the arsine, sulf. This may be and other materials, for example, not pure arsine sulf, but with germanium, with marganetes, with erbium, we have obtained to vary the properties. And we use the two sectoral apertures to obtain in one region. To obtain in one region all the nanomultilayers with pure composition and with both composition on this, to compare the properties obtained in these materials. And then about direct surface relief grating patterning. Diffraction gratings can be produced by different techniques, many of them the holography, and maybe the optical or electron beam lithography we obtain and by this electron beam lithography. But in this work we consider the samples obtained by holographically. And the two coherent beams generated in interference have the periodicity lambda defined by this formula, or this is defined by the wavelengths of the recording and the beam between the two recording beams, or reference and object beams. And in this case, we have to distinguish two forms of holography. This is intensity holography resulting in the surface relief grating, and the polarization holography with a periodic variation of polarization. resulting the polarization grating. And this is a setup of the recording. The main points of this setup and this polarization element, the polarizator and half-wave plate, which can allow us to vary polarization in each beam independently, and so to obtain different kind of the polarization recording on the sample. And this is a sample in which we write the grating in the nanomultilayer and on the each materials to compare the properties of these gratings obtained. And then once more about the polarization. You see, when you have the two beams, object and reference with perpendicular polarization, we don't obtain the intensity hologram on the surface of the sample, but we obtain the polarization difference, polarization modulation on the sample independence of the on the phase difference between these two beams, and the polarization resulting polarization may be different form from the linear polarization to circular and so on. And in this I show you, this is a sample and the two beams which record, and this between these two beams, this is a angle for the recording and the angle between the phase. But the angle between the polarization may be different for this. For example, for the intensity interference pattern, we choose always the same polarization in the both beams. For example, SS, this is a parallel to the surface of the samples. PP, this is a perpendicular to the wave, exactly to the wave vector, and so the circular polarization with the same direction. But for the polarization interference pattern, we may obtain the hologram with perpendicular orientation polarization or state of polarization in each beam. For example, one S, other P we may obtain, and for linear polarization between the beam on polarization is 90 degrees, or circular right-left polarization. When in this case we don't obtain the intensity polarization hologram. And this the sample of the grating which we obtained from the atom force microscopy, in which we write on our samples. So you see the very good quality. This is a profile of the grating, very good quality of the samples. And this is for different composition, not pure arsenic sulfur, but with germanium, and in this case with marganates. We obtain the good quality surface relief grating. And one more result, which I have to note, that before the recording, we obtain the surface with enough roughness of this surface, up to 10 nanometer, and we see the profile of the sample before the recording. But after recording, when we have the grating of this, we obtain the pure profile of this grating. We enhance the optical quality of the surface by the recording. And then I want to say that two main types of surface relief grating induced by holographic recording due to excitation by the light we can obtain. This is a small scala surface relief grating induced by either volume expansion or shrinkage or to difference response of the materials in the bright or dark zone in the interference pattern form. And vector surface relief grating induced by lateral mass transport in these materials. And up to now, the investigation of photo-induced mass motion in soft organic or inorganic polymer films was mainly based on the study of surface relief grating formation upon the illumination with the interference pattern. And the kinetic of this surface relief gradient growth was monitoring by measuring the diffraction efficiency in different polarization state configuration. On this slide, you can see the comparison between the surface relief grating recording on the nanomultilayers. This is the first graph, and we obtained the diffraction efficiency up to 30% on these materials at the polarization holography. And in this, in comparison, the same obtained in the same regime the pure arsenic sulf, and we obtain maximum the 12%, and other form of this behavior of diffraction efficiency for the pure arsenic sulf and for the nanomultilayers. And once more, again, this is obtained in the same technological conditions. And on this graph, I show you the kinetic of diffraction efficiency in different state of polarization. This independence of period of the grating, we may obtain up to 45% at the polarization plus minus 45 degree or light right circular polarization. We may obtain the diffraction efficiency of the grating. And in the case of PP, this is intensity hologram, only 25%. And in all of this case, we obtain the direct one-step recording without any additional treatment of the samples. This is a all optical recording process. And this we choose that this is a minimum at the 1 micrometer period, and this is the maximum diffraction efficiency and this period of the grating. And this comparison, the diffraction efficiency of vector and scala recording for different period of holographic grating. And from this you can see that the diffraction efficiency behavior is different for the PP and for the polarization recording. And from the around the 1.4 micrometers period, the behavior is changed. We have maximum and then the decay of this diffraction efficiency. And we can't see this on the PP holographic recording, but the maximum we stop this recording because after this there are the decay of diffraction efficiency, so the erasing of the grating of the materials. And surface relief gratings are interesting for large-scale application, and since they can be reproduced relatively easy without wet development as a master or without master directly from the chalcogenide glasses samples. And classically, isotropic grating can be categorized as thick or thin. Thick grating shows the Bragg diffraction. The diffraction efficiency can be approximated analytically using Kogelnik's couple wave theory, which is valid close to the Bragg angle. Thin isotropic gratings show Raman-Nutt diffraction, and they are classically treated with scalar diffraction theory, and their far-field diffraction efficiency are approximated using the Fraunhofer approximation. And in this, there are the as named Klein parameter, which define the thin or thick grating, and when this parameter Q less than 1, this is a thin grating, and when this parameter more than 10, this is a thick or Bragg behavior of the gratings. In our case, the Bragg behavior of the gratings is characterized by only 3 diffraction orders. This is a 0 and plus and minus 1 diffraction order. And the Raman-Nutt behavior is characterized by many diffraction order, the 2, 3, and much more diffraction order which we can appear. And in this graph, we can see that we see the many diffraction order on our gratings at the polarization recording, because and on the different thickness of the component composed of these nanomultilayers, because the thickness of each nanomultilayer, this is other main parameters which depends on the behavior of the grating. And then the estimation of Q parameters for our nanomultilayers was shown that we can consider the holographic grating as a thin grating for the period lambda more than 1.4 micrometers. And the holographic grating with period less than are intermediate grating. This is a not proper thick, but not as thin, because the Q parameter lies between the 1 and 10. But it concerns only the polarization holographic recording. And the efficiency of the diffraction efficiency of the holographic grating describes of this equation, in which we can see this is a Bessel function of first kind, and the parameters of this is a refractive index, this is the thickness of the layer, and reading wavelengths. And so we have different behavior for the our gratings. When we have the same thickness, we have the same wavelengths of the reading, and so we can propose that we have the difference in the refractive index of the materials, because refractive index of the materials is, of course, other than in the pure, for example, arsenic sulf, or in the nanomultilayers arsenic sulf or selene. And in the paraxial approximation of diffraction efficiency of polarization gratings, this diffraction efficiency can be approximated of this formula, and from this you can see that in this we can obtain diffraction efficiency of the S0 equals diffraction efficiency 0 order equals 0, a diffraction efficiency of the first minus order close to the 1 in the determined conditions of the recording and of the obtaining the samples. And there, but in this you can see the stocks. As this is the stocks parameters. So we can we have to note about the difference in the refractive index or birefringes which we obtain in our materials under polarization recording. And this once more I summarize about the parameters which we obtain, and again I'd like to underline that we obtain the very high diffraction efficiency on the layer, about 45%, without any additional treatment. This is a very good results for the any recording media. And about the concepts, there are some concepts, but we consider only two concepts to understand the features of polarization recording in our materials. The first based of the using the electrophoretic forces. And the electrophoretic forces generated when a neutral molecule or particle is suspended in a non-uniform electric field. And this electric field induces electrical charges within the particle to establish a dipole. If a non-uniform electric field is applied, the end of the dipole experience unequal Coulomb forces, which results in a total non-zero imposed forces. This concept has been applied by Teteris to explain a photo-induced mass transport in amorphous chalcogenide films. And this model very good explain the result obtained in the one materials, for example, arsine sulfur, arsine selene materials, but this concept doesn't explain the difference between nanomultilayers and one composition multilayers which we obtain in our experiment. And there are other model proposed by Fritzsche. And in this model, on the molecular scale, the structure of chalcogenide glasses is strongly anisotropic. Even without specifics, the larger anisotropic structural units, such as rings, chains, platelets, or pyramids, which characterize these materials, which may define the local structure or medium range order or particular glass composition. It is clear that one needs a volume containing a considerable number of atoms and find the optical anisotropy in microscopic samples. And we consider all of this model, but note that all these models suppose the creation of anisotropy in the materials. But the reason for appearance of this anisotropy is different. This optical anisotropy is induced by exposure of polarized light for illumination. And this conclusion summarizes all of this result, which I have said this, I don't repeat this. And this is all of my presentation, and thank you for your attention.